Hi guys, I wanted to go ahead and since we had that little bit of glare issue, I thought I would go ahead and tape section 2 from the samples of the conversion problems that we talked about yesterday in class. And I took from the other side that I can see good and clear. There's a little bit of one, but it is clear to see here. But I left right off at the slide that I was talking to you live in class about with the prefixes. Okay, this is a little bit of review, okay, talking about the metric system, remember base 10s, all right? So you have your, kilo, mega, and giga, 1,000 units, 1 million, and 1 billionth, okay? And this is straight from your slides, but what I wanted to get to was the actual first math skills when I was talking to you about conversions on how I was going to teach you today on Friday, because Friday, okay, because this is a B day. Right? And Friday's assignment was those 20 problems were restricted from the metric system, where we were just old school, moving the decimal point, which is perfectly fine when you're in the metric system. So when I'm going from meters to centimeters and I'm going from left to right, the decimal point moves those many places to the right, and I have the zeros. Okay? Remember, if I have a larger unit on the metric scale, okay, and I'm going to a smaller unit, my answer is going to get bigger because it takes a lot more of the smaller units to make the bigger unit. And vice versa, if I'm going from a smaller unit, say millimeters, and I go all the way over to kilometers, I'm going to be moving the decimal place each to the left, okay, which it's going to move the decimal point to the left, which is going to make the answer smaller because that's a giant unit and it takes a lot more of the little guys to make a big guy, so you're going to have a lot of times a value that's going to be less than a whole number, okay? So moving that left, moving that right, that's what I asked you guys to do for yesterday in class. This is Wednesday, as I'm making this part of the PowerPoint for you, and I'll have a couple other presentations for you too as well on how to do, but I want to walk you through this part of the math skills, all right, from the PowerPoint, and then I will go over in a separate one on some sample problems, okay? So in math skills and conversions, okay, if I have a roll of copper wire that is 15 meters of wire, okay, what is the length of the wire in centimeters? Okay, yeah, now I realize this is in the metric system. In the metric system, all right, and I can move the decimal point, you can use that to check, but we need to learn how we need to move using this for conversions, because not always are we going to have units of measurement that are in the metric system. You might have, this might have said feet, and I needed to go to meters, okay? Well, that's two different units of measurement, as I said at the end of class yesterday. And you cannot do the moving of the decimal point when you're comparing two different measurement scales, okay? Or that's like taking apples and oranges, two different things, comparing two different things, okay? So, all right, so here's your given. You have 15 meters. The length in centimeters that's what we're looking for, okay? So, first things first is what we do. It says, looking at the table of prefixes used from small measurements, you can find that 1 centimeter is, like I showed you, and it's the top of your worksheet, is 0.01 1/100th of a meter, okay? So this also means that 1 meter is equal to 100 centimeters, vice versa, depending on whichever it is. 100 of these makes 1 of these, and 1 centimeter makes 0.01 meters, okay? Just like in your PowerPoint, all right? So basically, you will multiply because you are converting from a larger unit, okay, meters, to a smaller unit, okay? And when we multiply larger to smaller, the answer is going to get bigger. Okay? If it was the other way around, we would divide and the answer would get smaller. Okay? So that's just a simple way of me hearing my voice if you interpret how it states it here. Okay? All right. So what it's basically saying here is you're going to, the length in centimeters is equal to meters times 100 over that. So what that's saying is 1 meter is equal to 100 centimeters. Okay? Or 100 centimeters over 1. Okay, that's the right ratio. 1 meter equals 100 of these, and 100 of these equals 1 of these. Okay? So that's what they're saying here in 3, when you write out the equation. And I will show this to you in other sample problems. I'm just walking you through the PowerPoint that you have. Okay? All right, so then what it does is, I call this the given. This is what was given. You were given 15 meters. Okay? And it was asking you to convert that equivalent to centimeters, all right? So, first rule of thumb is a lot of times they say you insert the, so I say this is the given, all right? And you put that over 1, all right? if this is confused like that. So one thing you can add in here is that over 1, like a fraction. It's still 15, right? 15 over 1, okay? Then what you do is you think, okay, I'm going from meters to centimeters, which is right next to it, okay? So it's 2 places over. So one of the things you need to make sure if you're confused on one thing is you want to make sure the unit of measurement that you're converting is across or diagonal from it. So that's how I know my meter goes on the bottom, which is 1 unit, and what's equivalent to 1 meter is 100 centimeters above it, okay? So then when I have the unit here that I'm converting it to, I know I'm ready to finish out the problem. So first things first, I had the given, I put it over 1, and then I put the conversion, making sure that, see, you got meters, and I noticed that 100 centimeters converted to 1 meter, it's the same, okay? So now what I can do is I cancel, all right? Just like simple fractions in math. So you see here it's cancel, cancel, so that leaves centimeters as my only unit of measurement, okay? All right? Here is my rag. Can you wipe that off? 1 second. Oh, got it. I was looking for that. Okay? So I have 100 centimeters over 1. Cross those out, just like you did here in the problem. And what that's leaving is telling me that I'm going to have, now I just finished the math. So now it turns into a multiplication division problem. So I just follow straight across. 15 times 100, okay, is 1,500, okay? Crossed out. 1 times 1 is 1, so isn't that 15 over 1? So my answer is 1,500. And my unit of measurement, I cannot forget my SI unit, is centimeters, okay? So let's see what this says here on the problem. Oh, look, that's the exact problem. I showed you the long division, so basically it's 3 steps. You write the given over 1, okay? You make sure you figure out from the metric the conversions, all right? We know that I need meters, so meters has to be here. So if 1 meter is equal to 100 centimeters, okay? And once I have that unit, I know that's what I'm converting to. I'm done with that. Then I cancel out the like things. In this case, meter, leaves me centimeters. And then I finish the math. 15 times 100 is 1,500. 1 times 1 is 1. 1,500 divided by 1 is 1,500. Centimeters, there's my answer, okay? Now, like I said, it's not hard. It's 3 simple steps. Given over 1. Write out my equivalents, right, and my powers of 10 until I have my unit of measurement in this outside fraction. I cancel, then finish the math. Times everything across, and then divide. Answer, whatever is my last unit of measurement left here in the problem, goes right there. There's your answer, okay? Erase this, okay? Move on to the next one. Okay. All right, so that was going over the simple problem. So I'm also going to talk just, might as well finish out the section 2 PowerPoint. So, units of measurement can making measurement. Many observations rely on quantitative measurements. Quantitative, remember quantity, as I told you in the definition, means the number part. Qualitative would be the definition. I use that example of photosynthesis. If I gave you the definition of photosynthesis, taking light and converting it, that's the qualitative version of it. The quantitative would be the equation, C6H12 plus O6 plus O2, presence of light. So this is, when we talk about measurements, we're talking about the quantitative, things like length, mass, volume, and weight. All these things are classified as quantitative measurements, okay? All right, here's a little video to watch here. Go ahead and play it.
Volume is defined as the amount of space occupied by an object. The volume of a solid, like this cube, may be measured in cubic meters or cubic centimeters. The volume of a liquid is often measured in liters or milliliters. 1 milliliter is equal to 1 cubic centimeter. The volumes of irregularly shaped solids can be measured by the amount of liquid they displace. For example, this rock's volume can be measured by dropping it into the graduated cylinder and reading the new liquid level.
So a little review
the
on
volume of a gas can be measured by measuring the volume of the container it is in, because a gas will expand to fill its container.
Okay. So that one example there, that graduated cylinder, okay, was showing you that perspective. Okay, so then real quick now we'll finish section 3, okay, which was just how we use graphs and so on. Just basically shows us line graphs, bar graphs, and pie graphs, a visual effect, getting the data, how we can see it. And a lot of times then the data, then we can pull the information from what we see, the x and y axis and whatever the topic is it's comparing. We'll use scientific notation and significant figures in section section 3 of chapter 1 that I'm also going to teach you to as well. Okay? And we're going to identify the significant figures in calculations and understand the difference between the term precision and accuracy. So this is just a straight definition comparison, but we'll have a little bit of formula stuff to understand how sig figs work, and then we'll have a little bit of scientific notation as well. Okay? All right. So we skip the bell ringer, and let's get to line graphs. Okay? So just simple value. Basically, a line graphs are best for showing continuous change. That's, you know, that graph that's going up and down, kind of like a wave or something like that. Right? So line graphs are usually made with the x and y axis, and I'll show you an example. They show the independent and the dependent variables. Okay? Remember that the dependent variable depends on what happens in the experiment. So that's what you're, you know, observing. Right? That's what you're recording. Okay? The independent variables are set before the experiment. So that's kind of like your constant. Right? So this is what's creating your data. And this is what stays the same. So you know that this is accurate. Okay? All right, so here's just a simple little line graph. You know, here's your time in seconds. They're comparing the volume of a gas, and over time, 0 to 90, this is what the volume. So they noticed as time increased, the volume of the gas was increased in this time frame, and this is what it went to. So it was plotting these points. So we did our x and a y axis. You had your volume on this side, which was changed, and your variables here, x and y axis. So you plotted, the first one, 0, 0, there's your starting point. Then we went to 10 seconds, and we plotted a volume of 3, made a dot. And then 20 seconds, and plotted 6, okay? And so on. We plotted each one of these points, and then we connected them. So without looking at this, when looking at this table, you go, all right, that shows me nothing. But as soon as you look at this graph, you say, oh yeah, I see. As time went on, the volume increased of the hydrogen in milliliters over time. Okay? And that's what a line graph shows you. It shows you that it could have fluctuated up and down and so on, but that's what line graphs are good to show you that gradient change over time or so on. Okay? So that's what line graphs are good for. Okay? Bar graphs are useful for comparing similar data for several individual items. Okay? A bar graph can be made clear how large or how small the differences in individual values are as well. Okay? So depending on your scale, okay, you know, how you decide to break it down here, you can really skew or make this graph look pretty dramatic. So you have to be careful about a bar graph, all right? If it's in small increments and all of a sudden you see this big, whoa, a big change, but it really wasn't much, you need to make sure and pay what kind of scale do you have down here. And this one goes on 500, 0, 5, 1000, 15, 2000. And this is the temperatures that they melt. Here are the individual substances. They color-coded them nice and neat. So just quickly looking at this without even knowing, and the graph is then, what are the melting points of these metals, aluminum, gold, iron, lead, and silver. The data's over here, okay? Even without having to look for the largest number, we can look right here and see that iron has the highest melting point, well over 1,500 degrees, specifically 1808 degrees Kelvin, iron melts. I can real quick look and see that lead has the easiest melting point. So it's a little over 500, or specifically, I can look over here at the actual data thing there, and lead is 601 degrees Kelvin. Okay? So it's easy to see this melts first, then looks like silver melts before, aluminum melts before silver, silver, gold, and that order. Okay? So bar graphs are easy to see quick data like that and compare things. Okay? And then pie graphs, all right, are a good example of showing the whole of something, 100% of something, okay? So if you notice, when you add up these three numbers, they add up to 48, and 40 is 88, plus 12, 88, and 12 makes 100. So it's when you're comparing the full percentage of something, like let's say, if you could do this with, like, say, your salary. If you ever seen like a a paycheck thing. Let's say you make X amount of dollars a month and you want to keep track of your expenditures and see where all your money goes. You could say, all right, I spend this much on gas, this much on food, this much on, entertainment, so on, and you get an idea on where all your money goes, and then you have X amount left over, and that helps you budget. You can use a pie graph is really good for that if you're comparing to C and you want to see really where everything is going. So a pie chart is ideal for displaying data that are parts of a whole. Data in a pie chart is presented as in percentages, okay? So bar graph, line graph, and pie graph, okay? 3 different types of information, and there's not one perfect way. Some graph styles are better to show certain data, but you can use various different graphs to show similar type of data, but it just depends on which one best to present. And they're always good at presenting and showing those because pictures are awesome, right? This is easy to cipher out and say right off the bat and say that in this particular case, oxygen has the highest grade of percentage, almost half, 48%, almost half of the total is made of oxygen. And then you got your calcium and carbon as the list. So it's easy to see that, okay? Okay, all right? So, scientific notation is a big time review, all right? As you know in science, you get really small numbers or sometimes you get really big numbers with lots of zeros or decimal points between them. So scientific notation is something you practice and we'll be using throughout the whole year, but practicing to display your answer in scientific notation, okay? So basically it's a method of expressing a quantity as a number multiplied by tens. The metric system is base tens, okay? So like for example here, if you have 10 to the third, that's 3 zeros, so I'm gonna add, that's 1,000. 2 zeros is 100, 1 is 10. If I have to the 0 power, that's the same as just saying 1. If I have -1, now I'm decimal points, okay? So I have a decimal, I move the decimal point to the left. -2 would be here, 1, 2. 3 places, 1, 2, 3. So these are all values that are less than the value of 1. Okay, so negative exponents up there in the scientific notation means I'm going to have a very small number. If this was -8, then I would take and move my decimal point, which I will show you in practice after this video in how-to videos on scientific notation. Okay? Okay. Whoops. All right, so using scientific notation, when do you use scientific notation? In calculations, when you follow the math rules for powers of 10. When you multiply 2 values in a scientific notation, you add the powers. Okay? So I'm going to show you the math problem. So what it means, if I had 4 times 10 to the 4th, times 10 times 10 to the 10th, I'm going to add those little exponents up at the top. Okay? Add them, right, for the powers of 10. Okay? All right, so here's a little math skill practice, same one in your PowerPoint. Okay? Oops. So it says, writing scientific notation. The adult human heart pumps 18,000 liters of blood each day. Okay? That's cool data, but this right here is just something to know, but this is what we're focusing on, the 1,800. Okay? This is what we want, 1,800 liters. Okay? Liters is volume, okay? That's the measurement for it, base unit, each day. Great. So write this value in scientific notation. So if I have 18,000, okay, I'm just writing it big so you can see it here, and it's asking me to put that in scientific notation. Don't, if I have my reference point here as my decimal point, isn't that, putting that there, it's still, I'm not changing the value. Think of this as dollars. If I put the decimal point there, that's still 18,000, right? Okay? So it wants me to change the scientific notation, so here you go. You move the decimal 1, 2, 3 to the last 2 whole numbers you have in the problem, or to ones and tens place. You see these are 2 whole numbers, 1 and 8. So I moved it 1, 2, 3, 4. So that is 1.8 times 10, and since I went to the left, it's going to be a positive exponent. 1, 2, 3, 4 times 10 to the 4th. Let's see if that matches up with my answer when it comes out. Okay, 1 times 8, all that math. There it is. Okay, okay. They walked you through a lot of the values there, but you said when I write 10,000 as the power of 10, 10 to the 4th, 1.8. Okay, they took it like that, but I just real quick, I just summarized all those slides. You're just going to take that value, and if it's asking you to convert it into scientific notation, and it's a positive value, that's all I did. As I went, notice my answer here matches up with exactly what they said. Oh, and then look, I did make a mistake. I forgot liters. Don't forget your SI unit. 1.8 times 10 to the 4th liters is the same value as this, because I asked you to put it in scientific notation, okay? All right, erase that out of the way so don't mess up the next slide, okay? All right, and we're gonna do some sample problems with it as well in practice, okay? We don't need this video because I just explained it, okay? So here's another using scientific notation, okay? All right, so, all right, your state plans to buy a rectangular tract of land measuring 5.36 times 10 to the 3rd. So this rectangle shape is 10 to the 3rd measures this. Okay, awesome. Rectangular tract of land measuring 5.36 times 10 to the 3rd meters by this. So that is estimated that. So it is telling me that it's 5.36 times 10 to the 3rd by 1.38 times 10 to the 4th. So that's basically telling me this distance is here and this distance is here because it says it's rectangular. All right, so I'm just a little visual kind of showing you here. All right, so what is the area? Oh, there's a little simple formula. What is the area of this tract of square meters? So area is length times width, as it showed it earlier. So this is my length times my width. So I'm going to times those two numbers together. So there's my length and width. Width here, length, okay? Two values, all right? And it wants to know what is the area. So basically, I'm going to then just times these two values together. Okay? Everybody see that? That's the nice thing about the video is when I erase it, you have it as I go to the next slide. Okay. So that whole notion there, so there it is. Area equals length times width, just like it showed. L times W, length times width. So here's my rectangle. Length times width, okay? Length, 0.36 times 10 to the 3rd, and width, 1.38 times 10 to the 4th, okay? I'm gonna times those two together. Here it is showing it to you. This times this. So when I regroup the values, remember what it said, all right? I'm going to add those exponents. When I'm timesing, all right, when I'm multiplying the values, the exponents get added together. So 4 and 3 makes 10 to the 7th, right? And then I times these two values together. So that's where I got it. If I took 1.38 times 5.36, I got this value right here, 7.3968. Okay, using your calculator, you can do that, all right? So I wrote it out that, I times those two together, and then like I said, it shows right here, I add the exponents. I added 4 and 3, and that's where I got my 10 to the 7th. And of course, my unit of measurement is showing the square. M squared is a way of showing that that's the square root, or that's the area, right? So basically what that said is, by measuring these two, that showed how many square foot, okay, or area I can cover in this, okay? That makes sense, right? I'm length times width, the two values, those times together, that gave me that. Then the two exponents, 10 to the 3rd and 10 to the 4th, is 10, and I just add the little exponents, 4 plus 3, that's where I got 10 to the 7th, and then it's m squared because I had meters and meters. M times m is m squared, okay? All right, so that was the sample problem in the notes, all right? And there's the problem. There's the answer, 7.4, okay, times 10 to the 7th. Now notice this, we haven't talked, but they rounded. We're gonna practice rounding, but we haven't talked about it, but it's commonality. See right here we had the 0.3968, it's okay. I'm not going to count off until we're going to do one thing at a time, all right? If you went ahead and rounded it to 2 places past the decimal, that's perfectly fine, which that's where you got the 9, it rounded up to a 4, that's why they had 7.4. This is the same as this value. And right now, okay, we're just going to baby step with this. We're not going to stress. If you rounded it, awesome. If you did and left like that, that's fine too. And notice the 10 to the 7th is the same, like I said, m times m squared, okay? So practice rounding, okay? Hopefully you still remember that rule of math. If not, we will still be going over that too as well, okay? All right. Okay. So then the two terms call them precision and accuracy. Precision is just a straight definition, the exactness of a measurement, okay? Like basically hitting the bullseye. Accuracy is a description of how close a measurement is to the true value of the quantity. It's not a big deal, but okay, just understanding these two different definitions. We're not going to focus as much on that. It's just understanding the definition, okay, with a little visual aid. But our main focus is the conversions, okay, making sure we understand that. Reviewing and mastering the scientific notation. Recall on that. We've been doing it for a long time. And then an extra thing is we'll start focusing on the significant figures, okay? So significant figures is a style or process for decimal placement that determines the amount of rounding to be done in a precision measurement associated in science. Okay? Sig figs is what it's sometimes, we call it, instead of saying the whole word significant figures, you just call them sig figs, which is abbreviated sig, S-I-G, figs, just F-I-G. Okay? So that's a common, what we refer to it. Okay? All right, so accuracy and precision. This is just showing a visual aid here. For example, a little ring toss here. Good accuracy near the post would be here. Okay, would have good accuracy. They were consistent, and good precision. They were close together. B, okay, is good accuracy near and poor precision like that. So this would be, I'm sorry, A and B here. Okay, even though they were accurately off, they weren't precise because they weren't all together in the spot. Okay. No big deal, but hopefully that gives you a little visual explanation in this slide. And that was also the same last little slide, I believe, in 1.3. Okay, here's another example here. This is pure, if this is where I'm going for accuracy, but my precision was good because I was consistently off. Okay, so I would make my adjustment on that. Okay, this would be poor accuracy and poor precision. There was no pattern whatsoever. This was real far, this was down. I mean, I'm all over the place, so I don't have either one represented there. So it's just showing you 3 or 4 pictures to how you compare those two definitions, okay? All right, so we'll go ahead and play this one on action.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value. This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate. Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise. Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate. When looking at experimental data, precision lets us know the experiment was done carefully in a controlled environment. Accuracy suggests that the experiment has accounted for all factors that might affect the system being studied.
Okay, so that was just giving you a verbal and obviously some awesome little diagrams there of the use of precision and accuracy. Okay, all right, so the last thing in this diagram is the use of significant figures. Okay, so in science or in chemistry, physics, we always have very small sometimes or very large measurements. Okay, so you can get a lot of decimal places past like 1.457395. Oh my gosh, that's a really small number, but man, extremely accurate and precise because of the many decimal places or that it goes out to. All right. So when you use measurements and calculations, the answer is only as precise as the least precise measurement. That sounds like redundant a little bit. So the measurement with the fewest significant figures determines the number of significant figures to be used. Okay. So what that is saying is, all right, in math, okay, when we would be, for example, calculating the volume, and we'll practice this. This is not something we're going to do in a 5-minute little video. We're going to practice this because significant figures, scientific notations, and conversions are all things that we're going to use all year. So it's important these first couple weeks to practice this. You're like, my gosh, I feel like I'm in math class. A little bit, all right? So a lot of this will be review or taking what you know and just applying it here in science class, okay? All right, so if I here's my 3 measurements, I got 3.125 meters high, 4.25 wide, and 5.75 long. So basically what this is saying, is I have a 3-dimensional box. Not bad, okay? So height-wise, which would be this, here's my 3.125. Width, okay, would be this, I guess it doesn't really matter width and long. So the width of it would be 4.25, okay? And I got that. So then, and how long is it? 5.75. So what they're determining here is the volume. So they're wanting to know, write the answer with the correct number of significant figures and volume. Now one thing I will always give you is, you don't have to recall that, I'll always give you the formulas, okay? I will always give you the formulas, and you just will plug in the values to solve for, we can call it X or whatever, or for whatever it is the question is asking. And what the question is asking for us to calculate the volume of this room. I made a little 3D box. When the room is this high, this wide, and this tall. So the formula for volume, and I would give you that, would be length times width times height. So basically all I'm doing is I'm going to times these 3 numbers together. We can all do that. We can punch 3.125 times 4.25 times 5.75 in our calculator. We're going to get a big value, okay? All right? And in that value, there's my length. Did I do it right? Length, width, and height, okay? All right? So when I times all 3 of those together, I'm going to get what? M times M times M. That's where I get my M cubed. M to the 3 power M cubed shows volume, all right? So that's where that comes, okay? And we'll practice that, and I will always remind you on that, all right? Okay, so let's go to the solving part, okay? Let me get rid of these because they don't match up, all right? Okay, so volume is length times width times height, so I times those 3 numbers together. And I got this big number, 76.367187. Look at that, look how small, that's not really, I mean, this is just 76 and it's not quite 77, right? This is really, it looks like a huge number, but the decimal point tells me that this shows you that this answer falls between 76 and 77 cubic meters, all right? So it's asking you, please put your answer in significant figures, okay? So here's your first IE example rule of sig figs. The answer should have 3 sig figures because the value with the smallest number of the sig figs has 3. Okay, that didn't make much sense, but watch me right here. All right, the 3 values I times, here, here, and here. What it's saying is whatever my answer is, guys and gals, I'm going to round this to the least amount of sig figs in the problem. So we haven't learned the rules of sig figs, so I'm going to teach you that in another video, but for all intents and purposes, there's 3 sig figs here, 1, 2, 3. There's 3 here, and there's 1, 2, 3, there's 4 here. And it says the least amount, so that's why it says I'm going to round my answer to 3 sig figs. And so here's my giant answer. So here's my first 3 sig figs, right? 76.3, so that means in the rules of rounding, I look at that 6, and what the rule is, what? 0 to 4 stays the same, or 0 to 3 stays the same, 4 and up, round up, okay? So that means that this tells me the 6, I need to round this up to a 4. So that's where I got 76.4 meters cubed. Okay? All right? And I'm going to go over in another video the rules on how to apply for significant figures. We haven't covered that, but you kind of get a rough idea. Multiply and division is the least amount. You just look at the values. You just do the simple math, multiplication or division, get you that answer, and then you just got to look back at the values you used to solve that. And the least amount of one with the sig figs, when I teach you that rule, is in what you know to round that. Because 3, 3, and 4, the 3 was the least amount. I took my first 3 sig figs. That means I looked at the one next to it, and that told me to round up to 76.4. Okay? I'm going to skip that because that is exactly what I just told you. And we're not going to worry about this concept map. Okay? All right? And we're not going to worry about this standardized little test prep thing right now either. Okay? So this covers the PowerPoint from where I left off yesterday at the math skills for conversions. Then we went ahead and walked through that. I'm going to do some more on another video that I'll post for you. And then we just explained the 3 graphs. And then we reviewed scientific notation, went through the problems just like that so you could hands-on see that with the PowerPoint. And a basic overlay of sig figs, which I'm going to explain more on that on how that works, okay? So I'm going to stop this video, so this will take the place of that glare and live on that, so you can stop and start and watch, and this will help you with that, and you can watch these all the time, okay? So this concludes Chapter 1, PowerPoint, review, notes, and examples, okay? All right, be back with you in a bit.